Ta-da. All right. Still freezing. Nothing new there, I guess. We're going to start chapter 2 today. Chapter 2. Oops. That was sloppy. Oh, well. It's only going to get sloppier. Specifically, 2.1 is going to take us quite a bit of time. Okay, and so what I want to do is just a little bit of review from last day, because it was last week. And so who knows? All right, and I always like to do a little bit of review with some lines on this page. Oops. So in terms of review, we spent a lot of time talking about variables. We did talk about some other things, but for today, kind of like previously on Stat 124, we talked about variables and identifying whether a variable is numerical or categorical, and that's what we're going to focus on today. And so if we have a variable, then, or maybe I don't need to do the colon, then it's either going to be numerical or categorical. And we introduce some synonyms, right? Quantitative, qualitative, but we're just going to focus on numerical and categorical today. And what we're going to do in chapter 2 is we're going to talk about how can we visualize and how can we summarize each of these variables. Now, it's very important that we be able to determine what type of variable is, because how we visualize it and how we summarize it depends on what type of variable we have, right? And so in chapter 2, maybe I'll put it, okay, fine. I'm going to bump this down a little bit, give myself some room. So in chapter 2, we will discuss how to visualize and summarize numerically each type of variable. So we will discuss how to visualize and summarize a variable. The type of variable dictates what an appropriate visualization is or what an appropriate summarization is, right? Now in 2.1, that's where we're going to talk about numerical data. It's kind of where a lot of things are happening. There's a lot of things we can do with numerical data. Whereas remember, categorical data, we introduced just briefly in 2.2, and there's not a lot that we can do, right? We have whether a student is in first year, second year, third year, fourth year, right? What can we do? What could we possibly do? Well, how many are in each category, right? So then we're really only talking about counts in the categories, which we could visualize with bars. There, we already did 2.2. That's it. And so categorical data, there's not a lot that we can do with them. And so we're going to focus on numerical data because there's a lot that we can do. Okay. And what did we say? We said, okay, well, how do I determine if it's a numerical variable, right? If I'm interested in the average, right, then I would argue that it's a numerical variable. So if we are interested in the average, which today we're going to start calling the mean, because in statistics we call it the mean, but just being able to move between the two is really good. So we're going to talk about the average. So if we're interested in the average, the variable is numerical. right? And that's going to be your argument. It's numerical because I'm interested in the average. You can use the reverse and say, well, I'm not interested in the average, therefore it's categorical, right? So you can use it on the flip side as well. So I'll call that the end of the review, but any questions before we start some new things? Okay. Just do a little, the end. No, the beginning of the end. No. Just briefly, it's kind of part of the review. We talked about scatter plots last day, but here's kind of a fun scatter plot. So Gapminder has all this world data that you can play around with, and it's interactive. And so you can change the year. This is set to 2011 because it's static, right? But as you change the year, you can watch the relationship change, right? And in this case, we're talking about, just always cracks me up, children per woman, which we're using as a measure of total fertility, and then the life expectancy in years. Now, from last day, we talked briefly about, okay, if I have two numerical variables, which I have here, we can talk about the relationship between these two. In fact, we would talk about, are they associated or are they independent of each other? Right. And so broad strokes here, looks like there's some sort of relationship. Okay? And so we would say that there is a relationship. So they are associated. Can use those two terms interchangeably. In fact, it looks like it's a relatively strong negative, and then I'm going to throw in linear relationship. We're not going to come back to this until the very last chapter, but it's nice to see it now in the beginning. But then we parking lot it and we don't see it for a long time. But the relationship looks, maybe I should say, I'll just stick to strong. Strong, negative, and linear. I say linear because it looks to me, there's no other shape that I would use to describe this. If I had to just overall generalize what this thing looks like, I could fit a straight line and it would do a decent job, right? And so we could have nonlinear relationships, but in this course, we focus on linear relationships. And we said, okay, because as x is increasing, y is decreasing, we have a negative relationship, or you can just look at it and kind of intuitively say, oh, it looks negative, right? And so here, there's a follow-up that I should have cut, but was the relationship the same throughout the years or did it change? I encourage you to go and check out the website. We're not going to do that, right? But check out the website. And if you do, you'll notice that it changed. You don't have to. It's just kind of fun to play around with. And so, and they've got all kinds of different variables to play around with. Okay. So there's the official end of the review because we talked about scatter plots the last day. Where we're going to start is kind of weird because we introduced these not as common plots before we introduce histograms. So what I want to do here is just make a note that for numerical data, the visualization that we should use is a histogram. Okay, so this is kind of just introducing some other things. And then, but here, for numerical data, we usually visualize that doesn't really make sense, but I think you get it. We usually visualize with a histogram, which is introduced later. But I just don't want you to be thrown off by these other ones, right? It's just nice to see some other options. They all do the same thing, and so it doesn't really matter. But what we're trying to do when we visualize a variable, right? We visualize a variable to look at the distribution usually, or to describe the distribution. To describe the distribution of, I'll say, of the data. So we want to know, okay, what does the general shape of this thing look like, right? And we'll throw some other things in there for the distribution, but in general, we want to look at the distribution. So a dot plot, what it does is it takes a very faint colored dot, and then as you have more observations on top of each other, the dots become darker and darker and darker. Okay, and so here, what this is going to look like, right? Let's say I look at this dot here. This is actually a bunch of dots on top of each other, right? And that's what makes it darker than these other faint dots. Arguably the hardest one to visualize the distribution from, but maybe it's fine. So what do we have here? Maybe you're good at it. I'm not. So I've got these faint dots leading up to a set of darker and darker and darker dots. And so if I have to visualize the distribution from this, what would I do? I would kind of break out these darker dots and kind of make them taller. And what it would end up looking like would be potentially something like this, something like that. We're going to have more useful tools, but this is what we're kind of aiming for. Whoop, hello. Let me just go mute everyone. Let's see here. Okay, there. I don't know why it doesn't automatically mute everyone, but it doesn't. Okay, so the reason I kept this slide is because what we want to do when we describe this distribution is we want to describe the distribution in general. So often we talk about the shape, but also we want to know about the center and the spread. So to describe a distribution, we have to talk about the shape, the center, and the spread. Right, to describe a distribution, we must discuss shape, center, and spread. So for each of these, we're going to spend time developing terminology around the shape, around the center, and around the spread. But for now, we're just kind of eyeballing it and using the best terms that we have available to us right now. Okay. So in terms of the shape, what are some things, if I told you that, okay, this is the shape that we're describing, right? We can talk about, well, there's a tail, right? A tail to the left, right? So that's part of the shape. What's another thing? I could talk about how many peaks there are. Looks like there's only one peak. And if I say that, then just close your eyes. I say, okay, there's one peak and there's a tail to the left, right? Does the shape that you're seeing in your mind look like that? Probably, right? And so then we've done it. And so here we say there's one peak. Well, I guess I should match the colors. Shape, one peak and a tail to the left. In terms of the center, what you want to do, and it's really difficult when you've got just kind of different colored dots to deal with, right? Our brains don't work that well. We're going to have better tools. But in general, you want to think of this as kind of a balancing scale. So where would the balancing point be? Well, let's say, only because I happen to know what the mean is, the average, which is the center. Oh my gosh, I've said too much. All right, you've kind of got this balancing scale, and that's going to be where approximately where your center is. All right. The center of balance, I guess. Center is at the balancing point. Roughly. Just rough approximations. Now here, roughly 3 point, well, this distance is 0.5. So 0.25, I don't know, 3.6. I know, rude. I happen to know it's 3.59, but that's not obvious from here, right? And so that's not something that I expect. But here I would say the center is around 3.6. And then I'll add, it's actually 3.59. Pat myself on the back. I did an awesome job. Oh, it's hard to know, but rough approximations, right? What are we trying to get at? Well, we're looking at the distribution of GPAs, right? And so when I talk about the center, right, what am I? Well, then I'm talking about the most common GPA, right? What's an expected GPA? Roughly around here, right? You don't want to say, oh, it's 4, right? Because that is not what this looks like, right? And so just a rough approximation, right? And usually it just communicates the scale of your data, right? If we're not talking about GPA, it might be something else. And I might tell you, okay, is it on a scale? Is it centered on something like 30, or is it centered on something like 300, right? Just gives me an idea of what this data looks like. Okay. GPA, we have a pretty good understanding of. So it's a nice place to start, I guess. For the spread, same deal. You really just want to talk about kind of a minimum to a maximum value, right? What are some reasonable values? Some of them are more extreme than the others, but in general, what kind of a range am I talking about here? So for the spread, it's roughly from the minimum to the maximum. So in this case, the spread is kind of between 2.5 and 4.0. Notice how sloppy that was, right? Doesn't matter. This looks like it's a little bit higher. It might be 2.6 or something like that, but I don't want to waste time. I want to say, okay, roughly 2.5. Anything less than that is kind of weird. If you get new data and you see something that's less than that, then that seems weird to me. Obviously, if you get a GPA higher than 4 in your new data set, something is wrong with that as well, because we know it can't, right? It can't be. And so knowing the spread, you just have a range of plausible values for the next time you get similar data. Okay. Now, I wanted to do a little Oh, you can't see me behind the scenes here. I'm gonna move the next slide way, 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 way down. Even way more down, I guess. There. Ta-da! And we go way back up again. Sorry. Whee, so much shape. Center and spread. Okay. So another way to visualize this is through a stack dot plot. Again, not that helpful because what we're going to be working towards is something like this, a histogram where we've got these nice clean bins, okay, but they behave the same way, so it doesn't really matter, right? But a stack dot plot is exactly what as it sounds, right? You stack the dots instead of layering them on top of each other. Arguably, this is improved over the regular dot plot, but still not as nice as the bars of the histogram, right? But, well, only because I gave you a sneak preview, right? But what would we do? For the bars of the histogram, then we create bins and we stack each individual inside those bins, and how many we have inside the bins, right? That's the height of each of the bars, right? So I guess I can jump there right away. But here, let's just congratulate ourselves because we were able to sort of see that that was the shape from just the dot plot, right? This is easier, but we were able to do it. Okay. So now, right, we will use histograms to visualize a numerical variable. So those other guys were fun, the dot plot and the stack dot plot, but ultimately we're only going to work with histograms, a numerical variable. So the idea with histograms is we're trying to visualize the distribution of the data. And so if we talk about this data set here is the hours per week spent on extracurricular activities, right? And so that's our numerical variable. And now our goal is to try to visualize and describe this distribution. Okay. Now, a couple of terms are, okay, so I've got, well, they talk about the data density, but really what we're talking about is the count in each of the bins. Okay. And so anyone who reported between 0 and 10 hours per week spent on extracurricular activities, they make up one part of these bars, and then we stack them on top of each other. So here we're going to have a count on the x-axis, or often it's called the frequency. And then this is a bin, right? So we've got multiple bins, and some bins are empty, which is fine, right? Because there was no one who, so here it's very, very tiny, 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 right? But it looks like no one reported spending between 50 and 60 hours per week on extracurricular activities. And this one makes me exhausted just looking at it. 60 to 70 hours, either super fun or, well, exhausting. I don't know. So, but most of our people in our data set, presumably, are somewhere between kind of 10, 20, 30, right? Really tapering off quickly. Yeah. And so what we're going to look at is, well, what if I change the bin width? And so the bin width is kind of this tricky balance. And it's something that I'll get you to play around with in the lab next week, where you play around and change the bin width. And for me personally, I'm not concerned about revealing too much about the data, as long as you're okay to generalize about the data. Okay, so I'll tell you what I mean. But I am concerned about hiding too much information, right? So here, this first one, well, first we can figure out what the bin width is. Looks like the bin width is 50, right? 0 to 50, you're in one bin. 50 to 100, you're in another bin. Well, that tells me nothing. And so I don't want it, right? This is bad. Bad, right? Let's say the bin width is 50. I'm not saying a bin width of 50 is always bad, but for this data, right, then it's bad. Sometimes it's an excellent bin width. So you got to play around with it. Moving across this way, right, because that's how the bin widths are decreasing. So now let's look and say, okay, I've got a bin width of 10 now. I see a little bit more of the shape emerging, so that's nice, right? And so I'm okay with this one. I'll say it's okay. Oh, and I guess I should tell you, I always forget to tell you when I'm marking, if you follow through on something, if it was wrong, but I'll write okay. So I write okay a lot, and that's, I guess, what it looks like. Looks weird. But what's the bin width? We said it was 10 here, right? It's okay. It's showing the distribution a little bit, well, definitely better than the first one. The reason I say it's only okay is because here I'm looking at a bin width of 5, and there's a little bit more kind of definition here. So I'm able to extract a little bit more information without it getting too nitty gritty, as in this one. Okay, and so this one I'm gonna say is great. Whee. Right, a bin width of 5 in this case. And we'll talk about this one before I tell you why this one, I think this one is great. Like I said, I'm okay with you having a very precise bin width or a very small bin width, as long as you're able to look at this and still generalize this to look like this, right? Or that was a bad one. Which when you're first starting, it's a little bit, it's very tempting to want to talk about this dip and this dip and this dip, right? But when I compare this distribution to this, right, I see, okay, I can get that general shape from this third option. And so this one is okay. The bin width looks like it's 2, 2, 4, 6, 8, 10. Yeah. But it's showing too much detail, right? That we would then have to smooth over. Showing too much detail, arguably. I'm okay with that one, right? But I don't want to see something like this. But no, I don't think you would do that, right? It's hard to describe it, or I guess it's really easy to describe the shape. And so you're going for something like this. In general, where is it? Okay, fine. When you're describing the distribution, I always think of it as just kind of draping a sheet over it. So you don't want to get into too much detail. And so that's why you want to be kind of careful of things like this. Because if you drape a sheet over it, right, then you wouldn't care about this dip. Huh? So when we said we started our journey and talked about the shape of the distribution, we said, well, I could talk about the peaks, right? And so those peaks are called modes. So a mode is a peak in the distribution. So when we talk about the shape of a distribution, we're going to talk about the modality. And so the mode is going to be how many peaks do I have, right? And so most of the time, we're going to be talking about a unimodal distribution, uni meaning one, and so there's a single prominent peak. That's going to be your most common one. You might find that there are several prominent peaks. So if there are two, we specify that it's bimodal, right? Or if it's more than two, we say multimodal, right? And then on the flip side, if there are no peaks, right, then you say it's uniform. Okay. And of course, we've got an example of each. And so what I want to do here is, this is the way cuter way to think about it. I say a sheet, but she says you you drop a limp spaghetti over the bars, and then that describes the distribution. And so drop a limp spaghetti here and see what we get. Something like that. That looks unimodal to me, just one distinct peak. It's only when we have something like this, I drop a limp spaghetti on here. Might look something like that, right? It has to be pretty cooked, right? And so here, this would be bimodal, right? I've got two distinct peaks. You don't want to jump on that bimodal train too soon, right? Because what you want to consider are things like, well, how big is my data set? You might have something that looks like this, but if you have a small data set, then you would argue that as I collect more data, it would kind of smooth out and become unimodal. So what gets strange is we talk about all these different shapes, but we're always going to be arguing that it's unimodal unless it's very obviously not. Okay. And so here, if I drop my spaghetti, I might have something that looks like this. I know it's supposed to be multimodal. I'd probably generalize it as just bimodal, right? Lump those two close ones together. But it's supposed to be an example of multimodal, so I'll take it. And then here, if I drop my spaghetti, kind of a stretch, but if I squint, I get this uniform distribution, right? There's no prominent peaks or anything like that. And so I'm going to call this a uniform distribution. Any questions about that? Okay. Now, if you have a unimodal distribution, which I just told you we're usually going to have, right? So if we have a unimodal distribution, we can discuss the skew. Low battery, but I'm plugged in. Oh my gosh. Thank you. That would have been a disaster. Is it charging? Oh, it's charging. Okay, crisis averted. Thank you. Let's see here. So throw me off. If we have a unimodal distribution, we can discuss the skew. The skew is that tail that we introduced in the very beginning, right? And so here, right, we said, before we had any terminology, we said, okay, it looks like there's a tail going to the left and there's one peak, right? So then now we're going to switch that terminology to say, well, it's unimodal and it's skewed. And when we talk about skewness, it's always skewed in the direction of the tail. Okay? And so here, it's always skewed in the direction of the tail. Which can be a little bit counterintuitive because usually humans in general want to talk about, well, this is where the lump is, right? But in statistics, we're concerned about those extreme values, right? What's going on with those tails, right? And so for us, the skew is always in the direction of the tail. Yeah. And so here we've got this kind of shape, right? And so I've got a tail to the right. And so this would be skewed right. You could also call it a positive skew and alternatively a negative skew, right? If you prefer. Again, I know what you mean. You're welcome to use either one. I tend to use right skewed, left skewed, or skewed to the right, skewed to the left. But you could call it a positive skew if you want. And what about this little guy? I've got a little bit of a tail to the left. All right, and so here I'm gonna say skewed left, or we could say it's a negative skew, right? Going in the negative direction. Just as long as you talk about the tail, right? It's the direction of the tail that's the skew. Our other option, right skewed, left skewed, or symmetric. So now, right, I've got a unimodal distribution, roughly symmetric around that peak or that mode. And this is a very special but also common shape that we're going to be working with. And so here, this would be considered symmetric. And I want you to just kind of rein it in. If you find yourself wanting to talk about, oh, well, there's kind of a little bit of a tail to the right here. No, broad strokes. Okay. And so if you can argue that it's symmetric, then that's what I want you to do. Okay. If you can argue that you have a unimodal symmetric distribution, then that is great. Okay. And what we're going to find is that it opens up a huge bunch of tools that we can use. And so that's why what we're arguing is always towards a normal distribution, which is a name. So I tend to capitalize the normal here. It would have been capitalized anyways, but a normal distribution is a uniform or a unimodal symmetric distribution, specifically with these tails, right? Kind of this beautiful bell shape curve. So I'm not supposed to introduce it here, but I think it's really valuable to introduce it early on. Yeah. And just like, what a triangle looks like. You know what a square looks like, right? A rhombus, maybe not. Right, but you know what those shapes look like. And so now I'm just adding another shape to your repertoire, and it is this kind of bell-shaped distribution, and it's called the normal distribution. And so in general, let's see if I can pull this off. Bink. Something like that. And I'll highlight it here because it is tricky when you're first starting, but they're all skewed in the direction of the tail, which is what we've said already. Okay. Good. When we're talking about the shape of a distribution, we also want to talk about any extreme values, so any outliers. And so here, outliers are extreme values. So we'd want to talk about those outliers. So when I describe this shape, I would say, okay, this one looks uniform or unimodal and skewed to the right, right? And so here, unimodal and skewed right with outliers, right? With some number of outliers. Now we could spend some time, right, and figure out the height of this bar. Is it 1 or 2? I can't tell, right? Roughly 2 maybe on a scale of 0 to 5. It doesn't matter, right? But I would say with a few outliers around 20. Here, how would I describe this shape? So now I would say, okay, well, what if I ignore these outliers for a bit? I'll talk about those separately. Then this looks approximately normal to me, right? Normal now implying this bell shape, unimodal, symmetric, right? And so it's this umbrella term that we're going to use. And so here it looks approximately normal. Oops. And then I'm going to say with the exception of some outliers around 90, right? 90 to 100. With the exception of a group of outliers around 90. Oops. Good. Well, we already did this one. But how would you describe this shape? Well, it looks skewed to the right. I'll move on to the next one. Kind of beat this horse. So I don't know why these are all cartoony drawn, but what we said, okay, so some common shapes that we're going to talk about are usually unimodal, but also we can have bimodal, multimodal, or uniform, right? Where it doesn't matter what the value is, it has the same probability of happening. Uh-oh, it's happening, the probabilities. If it's unimodal, we discuss skewness. And so it can be skewed to the right, skewed to the left, or it can be symmetric. And I'll just emphasize with arrows in the direction of the tail. Little recap, I guess. So one skill that's going to be really useful, especially if you're tackling data that you might not be very familiar with, right, is just knowing what to expect in terms of the shape, right? Because then you can say, well, that's not what I expected. And so which of these variables do you expect to be uniformly distributed? We're going to talk about the distribution or the potential distribution of all of these, obviously. And so we'll start with the weights of adult females. Now, kind of a phenomenon, I guess, is that things like weights and heights and speeds and just things like measurements that we make are usually normally distributed. Okay, and so this, I would expect a normal distribution, right? I always lift off there, sorry. Right, so I would expect a normal distribution. One thing, just as a rule of thumb, especially since you're in business, anytime you're dealing with money, we're going to have a skewed to the right distribution. Just traditionally, just a jumping off point is anytime money is involved, so I'll say kind of money is typically skewed right. If we think about salaries of a random sample of people from North Carolina, right? They live in the same region, fair enough, but even within that region, then wait, you might have probably something that looks like this, right? Most people making kind of a typical amount, right? Whatever that is, right? And then there's a very few number of people making a huge amount, right? There is kind of a lower end, right? And so that's what often creates this skewed distribution, is when there's no possibility for lower, right? But so traditionally, right, money measurements are skewed right, okay? And so if I go from that knowledge and say, okay, check in, does it make sense to say salaries are skewed to the right? Yes, it does, right? How about house prices? So again, it's money, right? Most homes sell in some kind of typical range, and then there are other homes, right, that sell for a lot more, right? But not very many of them. There's also kind of a minimum entry fee, so to speak, for buying a house, right? And so there's that lower end. Okay. This is going to be important because when we talk about, right, we're talking about shape right now, but we're about to talk about the shape or the center and the spread, and the shape is going to determine what the appropriate center and spread are, right? And so that's why, right, we need to know, okay, typically these are skewed, so then we would need to use a different measure of center. Okay. Whereas if we talk about the birthdays of classmates, right, the day of the month, so here I've got the day of the month, the first, the second, the third, blah, 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 blah. I would expect everyone to be born on the 3rd. No, that doesn't make sense, right? We understand that it's evenly or uniformly distributed across the days of the month. So then here, this is uniform. I'm sure there's some research that has been done and said that this is the most common day to be born, but in general, it's kind of spread out. And so it's uniform or evenly distributed. Good. So because we already did this for the previous one, I'm going to alter this activity, which we're not really going to do because I'm boring like that. just take the reins and I run with it. I'm going to change this to come up with a concise way to describe a distribution, or the distribution of any variable, changing it drastically. Yeah. But what I want to emphasize here is that to describe any distribution, right, we need to talk about the shape and the center and the spread. Just in general. So what I like to do is just imagine that you're, 90s commercial style on the phone. You're on your bed. Hey, what are you doing? Oh, I'm looking at this distribution. Oh, what's it look like? It's normal. Oh, wow, cool. Centered on 3. Okay. And the spreads between -10 and 30. I don't know. Oh, cool. What does that look like? We can draw it. I said the shape was normal, roughly. Centered on 3. Somewhere between, well, I guess I should have said something that made more sense for symmetry, right? Let's say -20 and 30. I'll bump it out a little bit. Okay. And so here, right, I've described this entire distribution, right? So that's why you need to talk about all 3 things in order to describe it. Of course, on test 1, I'll make you describe a distribution. And so you have to touch on all 3 things. Okay? But just rough approximations. Because we've spent a lot of time on shape, right? And so now we're going to spend a lot of time on center, and then followed by spread. Now, the shape, right? We said, okay, the shape of the distribution determines what an appropriate measure of center and spread are going to be. Okay? So what I'm going to add here is if the shape is normal, the appropriate measure of center and spread are going to, or let's say, let's start with center. The best measure of center is the mean, which is the average. And I'll put it on here, but it's going to take us a while to get there, but or maybe not, because I moved the slide, I'm just realizing. So quicker than I thought, maybe. And spread is either the variance, which is where we start, or the standard deviation, which you have probably heard kind of mentioned before, right? And so even if you don't know what it is or how to calculate it, we have some kind of intuitive definition of, okay, with a standard deviation of this, right, it kind of gives us some bounds on reasonable values, right? And so that makes it a measure of spread. Okay. This is if the shape is normal, and we're not going to get there today, I'm pretty sure, but if the shape is non-normal, so I'm lumping all the non-normal things together, right, doesn't matter, then we're going to use, should I say it now? The median instead of the mean, and we're going to use the interquartile range instead of the standard deviation. Okay, and so depending on the shape, that's going to determine which way we go. Okay. But let's start. I'll leave it there. I'll introduce it again next day. Okay, so the mean is what we use as a measure of center, right? So we can eyeball the center, right? Where the peak is, if it's normal. So for a normal distribution, we can calculate the center by finding the mean. Now, if I gave you a list of 10 values and I asked you to find the average of those, then I think you would do what? You would add them all up and divide by 10, right? Because you have 10 values. Okay. And so what I want to do is use that knowledge that you already have and introduce summation notation. Fun to say, fun to do. Have you used summation notation before? No. Okay, that's okay. I'm going to add a page here. So I have more. So what we're going to have in our data set are values x1, x2, all the way up to xn, because n is our sample size. So let's start there. N is the sample size. Oops. And ignoring the X bar for just a second, we are going to talk about it, but there's a lot of moving parts here in this very relatively basic formula. But what this looks like, I'll put it down here, is if our data set, so our data, we've got some variable X, right? So just a general name X, right? Height, weight, whatever. GPA, number of hours per week that you do extracurricular activities, it doesn't matter, right? And so I've got this broad name X, which means that I have observation 1 is going to be X1, X2, X3, and all the way up to Xn. Okay. We can kind of link this to a spreadsheet and just kind of visualize it this way. And if I asked you to find the average of X, right, you would add all these up and divide by n because there are n things, right? And that's what this is saying. Okay. Now, what we could do is we could rewrite this as the sum. Okay, so this is a capital sigma, and it's read as the sum. And just buckle up, bear with me, from I equals 1 to n. Now, when I read summation notation, I just ignore those, right? It just says add up all the things that I'm about to tell you to add up, okay? And so here, what this is going to be followed by in this case is x subscript I, right? Where I is going from 1 to n. So it's saying add up x1, x2, x3, x4, all the way up to xn. Yeah. So then divide by n. Yeah. And we're going to denote this by x bar. Now let's talk about x bar for a second. X bar is notation that we use for the sample mean. In fact, it's the sample mean of X. Sample mean of X. In general, anything with a bar over it comes from the sample. Why would we care whether it came from the sample or not? What's the alternative? It either came from the sample or it came from the population. But then we go back to chapter 1 and we say, okay, well, what we're doing here is we're taking sample information, such as a sample mean, to learn about population information, right? Which would be the population mean, right? I use the sample mean to try to learn about the population mean, but I can't use the same notation for both. That would be very confusing, right? So we need notation to denote that, hey, this came from a sample. This is something that I've calculated and I know about. And so here, anything with a bar over it is a sample mean, is a sample mean. Or the average, right? The sample average. So then my go-to, it's your average smiley face. Average smiley face. A little bit of stats humor. Okay. So then what are we going to use to denote that something came from the population? Well, we're going to use Greek letters. Okay? And so, and maybe I'll use green here, to denote a measurement, measurement, I don't know, is from the population. We use Greek letters. Also, we typically use Greek letters. There's one instance where we don't, but just broad strokes, we use Greek letters. We typically use Greek letters. So to denote the population mean, we use this Greek letter mu, which is kind of a fancy M, right? And so mu is the population mean. And if you're typing, it's easier to just write mu, right? And that's fine. Okay. And so mu is the population mean, and it's a capital letter mu from the Greek alphabet. Yeah. So then if we rephrase what we're trying to do here with statistics in terms of the mean, for example, right, is I use X bar to try to learn about mu, right? And so we use X bar, right, the sample mean, to learn about mu, the population mean. Yeah. In general, we're going to have what we call a statistic is something, so a measurement from the sample. Notice the S and the S, right? And so in general, a statistic is a measure, I'll say measurement, I guess, from the sample, while a parameter is a measurement from the population. Is a measurement from the population. So it gets pretty boggy in terms of the notation, right? Because we're always going to have some measurement from the sample, but we also have a corresponding measurement in the population, and we need notation to denote where things came from. In general, if it's something that we calculate, right, then it's from the sample. We don't know what the population is. That's the whole point of statistics, is we don't need to know what the population looks like. We only need the sample, and then we can learn about the population. Okay, so far, the only statistic and parameter that we've introduced is the mean, right? But I'll introduce another one real quick here. Let me go back here. Okay. What we're gonna do, the only thing I wanted to highlight here is that when we talk about X bar, for example, our sample mean, that's our best guess at what the population mean is, right? We've talked about it before. We understand that, okay, if I put my sample back in the population and I randomly select a brand new sample, I know that my mean would change, my sample mean would change slightly, but what am I also expecting? I'm expecting the values to hover around the population mean, right? And so that's one of the things that we're going to leverage. But what we're going to talk about is we're going to start calling the sample statistic, or the statistic, a point estimate, right? A point estimate from the population. It's a little while till then, but it's good to introduce it now. Okay. So the mean, if we have a normal distribution, is our best measure of center. And if we have a normal distribution, then the best measure of spread, we're going to use the standard deviation, but to get there, we need the variance. And so we'll introduce the variance, right? But they're related. So I'll start it here. So again, if we have a normal distribution, an appropriate measure of spread is the variance, and then I'll follow it up with or a standard deviation. I'll show you the link between the two, or standard deviation. We, in this course, are going to focus on the standard deviation, but the standard deviation is the square root of the variance. Spoiler alert. And so we need to find the variance before we can find the standard deviation, but they're related, okay? The standard deviation is just simpler in terms of interpretation, that's all. Okay? So we'll start with the variance. Uh-oh. Good thing we spent all that time thinking about summation notation and developing it from something that we can kind of link to, right? And so here, the variance, the sample variance, is denoted by a lowercase s squared. Okay. So here, wait. Oh, I'll add a page here. So the sample variance is denoted by a lowercase s squared. Okay. The population variance, I'm going to introduce it now, is denoted by a lowercase sigma squared. The population variance is denoted by lowercase sigma squared. So sigma is this little O with a well, this was kind of a weird one. Oh, with a little tail on it. So lowercase sigma squared. Remember, this is a capital sigma. How did it go from this to this? I don't know. I don't know. But this is a lowercase sigma squared. Yeah. Good. So again, we've got this, okay, statistic is S squared, parameter is sigma squared, right? But S squared is the point estimate of sigma squared, right? So it's our best guess at what the population variance is. But now let's talk about how would we calculate this? Now, to me, it's not important that you're able to calculate these things by hand. We have software to do that, right? But to me, what's important is that I should be able to give you a formula like this, and you should be able to pick it apart and know what it does, right? I don't want you to be able to do it necessarily, although it helps, right? And so we're going to pick this thing apart. Okay. And ignore the summation notation for just a little bit, right? And what I want you to do is just kind of find the center of this equation. And so inside all the brackets, inside everything. And so inside at its very core, I'm going to be looking at xi minus x bar. Okay. So let's start there. Ignoring everything else. And again, I'm going to highlight what my data set looks like. We've calculated the mean, right? So here we've got x1, x2, x3, all the way up to xn. I'll call it step 0. We've calculated the mean. So we have x bar already, right? We have the center. Now we're moving on to the spread. So then, first thing I'm going to look at here is xi minus x bar. Luckily, we've seen this xi notation before. And in this case, what's it telling me to do? Xi minus x bar. From each x, subtract the mean. What's that doing? It's finding the deviation from the mean, right? How far is each thing from the mean? That sounds like spread to me, right? What kind of spread am I looking at here? Okay, and so here, step 1, find the deviation from the mean, and I will clarify that, from the mean, which means subtract the mean from each data point. Subtract the mean from each point. But we're going to call that the deviation, so it's good to just get in that habit right away. Okay, so now visualizing the mean's at the center. We already established we have a symmetric distribution. And so some points, about half, are going to be less than the mean, and some points are going to be greater than the mean. So now I'm going to have positives and negatives. What if I add those all up? Well, they're going to go to 0. That's just how the mean works. So that's not very helpful. So how can I avoid just adding things to 0? I know there's spread, right? Because I was able to find deviation. So a spread of 0 doesn't really make sense. So one go-to move, I guess, is we can square those values. Squaring negative values makes them positive, but it also has an added benefit of kind of amplifying larger deviations, right? And saying, oh, these guys are bad, right? And kind of increasing your spread that way. So then here, now I've got xi minus x bar squared. I'll call it step 2. Square each deviation, right? So each of these steps for me, because I work slowly, I would make a new column next to my original data for each of these steps, right? And so here You're not going to do that. I'm going to make you do it in the lab using Excel, but it's not something that I'm going to make you do. So step 2 is square each deviation, right? And I'll write down why, right? It makes negatives positive and amplifies large deviations. Now we're ready to move on to the sum. Now add up those squared deviations. Sum from I equals 1 to n, which I ignore when I read it. It's technically there. Sometimes I don't even write it. Just the sum of these squared deviations. So now add up the squared deviations. This is going to become one number, right? The squared deviations. This becomes, or I'll say becomes, one number. Then we divide by n minus 1. And what color haven't I used? I don't know. Blue? How boring. End on blue. So now I equals 1 to n of xi minus x bar squared divided by n minus 1. Step 4, divide by n minus 1. We divide by n minus 1. It gives us a better estimate, and that's all we need to know. There's a ton of theory behind it, but for us, n minus 1 improves the estimate instead of what you would probably want to do is n instead of using n. But that's as far as we're going to take that. Okay. And so then you have the variance, and then I'll just throw it in here, but I'll use it for review next day. So then s squared is the variance, which is the standard deviation squared. So then the standard deviation is the square root of the variance. Ta-da. Which means that the standard deviation is the square root of sigma squared, which is just sigma. Ta-da. But I'll use that for review next day. If you have any questions, let me know. Otherwise, I will see you on Thursday. And I'm going to stop this. Oh, sorry.